We've talked about the bond strength of covalent bonds. Now let's talk about the bond strength of ionic bonds. Remember, ionic compounds are made up of a three-dimensional lattice of ions. Lattice energy is the energy that's needed to take that whole ionic compound and break it apart into individual ions. If we had an ionic compound that had the formula Mx, it would break apart into the cation, which we could represent as M, with an N plus charge, and X would be the anion with an N minus charge. The lattice energy is basically just Coulomb's law. We have the charges in the numerator and the distance between those charges in the denominator. That distance is the sum of the ionic radii of the positive ion and the negative ion. The greater the charges are, the greater the bond strength, and therefore the greater the lattice energy. The smaller the charges, the smaller the bond strength, and the smaller the lattice energy. With distance being in the denominator, larger radii, which correspond to larger distances, leads to a weaker bond strength. We can use Coulomb's law to tell us which ionic compound should have a larger lattice energy compared to another compound. In this example, we have aluminum oxide and aluminum selenide, and we want to find which has a larger lattice energy. One of the things to think about is the charges, which go in the numerator of Coulomb's law. Oxygen and selenium are both in group 6A, which means they both have a -2 charge. The only difference between the two compounds is the ionic radii, and therefore the distance between the charges. The oxygen 2- ion has a smaller ionic radius than the selenium 2- ion. Remember, ionic radius follows basically the same trend as atomic radius, that is, larger equals lower and left, as long as you're staying within the same category of either all cations or all anions. Since the oxygen ion has a smaller radius, it's going to have a smaller distance. Since distance is in the denominator, having a smaller distance means it's going to have a larger lattice energy. Therefore, the one with the larger lattice energy is the aluminum oxide, because it has a smaller distance between the ions. We can use Hess's law to calculate lattice energy by breaking down the formation of the ionic compound into steps. These steps make up what we call a Born-Haber cycle. We're going to use several different enthalpies in our calculation. One of those enthalpies is delta HF, enthalpy of formation of the compound. Another one is ionization energy of the metal. Remember, ionization energy is the energy required to remove an electron from an atom in the gas phase. Another one is electron affinity of the nonmetal. Remember, electron affinity is adding an electron to an atom in the gas phase. We're going to use delta HS, the enthalpy of sublimation of the metal. Sublimation is the process of going from a solid to a gas. D, the bond dissociation energy of the nonmetal, will be another of the energies that we're going to use. Finally, we'll be able to calculate the delta H lattice, that is, the lattice energy of the ionic compound. Here's a Born-Haber cycle diagram for cesium fluoride. This diagram shows all the different steps that are needed to make an ionic compound or to break it apart. We start with cesium fluoride solid, and our first step would be breaking it into individual atoms using the reverse of the enthalpy of formation reaction equation for cesium fluoride. The enthalpy of formation reaction equation would have the elements in their standard forms. Cesium would be found as a solid, fluorine would be found as F2 gas, and then cesium fluoride would be the product. Since we need the reverse of the enthalpy of formation reaction, we will use the negative of the delta HF value. For example, the delta HF value for cesium fluoride is negative 553.5 kilojoules per mole. So we will use positive 553.5 kilojoules per mole in our calculations. Our next step would be using the enthalpy of sublimation for the metal. The metal, cesium, is going from cesium solid to cesium gas. We could look up the enthalpy of sublimation value for cesium in a table, and finds that it is 76.5 kilojoules per mole. Then we would use the ionization energy of the metal. The metal cesium is losing an electron to become positively charged. It's doing it in the gas phase, so we can use our ionization energy, since the definition applies. The ionization energy value for cesium is 375.7 kilojoules per mole. Our next step is taking the fluorine molecule, which is F2, and breaking it apart into individual atoms. To do that, we need the bond energy, D, for the fluorine-fluorine single bond, which is 158.8. However, because fluorine has a coefficient of 1/2 in the equation, we need to divide the bond energy by 2 and use 79.4 as the value in our Hess's law calculation. Lastly, we go from the fluorine neutral gas to fluoride ion gas by adding an electron in the gas phase, so we can use the electron affinity of fluorine. Fluorine's electron affinity is negative 328.2 kilojoules per mole. When we add those 5 steps together, 4 of them positive and 1 of them negative, we get the overall delta H for the lattice, because at that point we have cesium ions and fluoride ions in the gas phase. The overall change in energy is 756.9 kilojoules per mole, which is the lattice energy for cesium fluoride. This slide basically takes what I just talked about and puts it into word form. We have 5 steps that go into this calculation. We're breaking the ionic compound into its individual elements, and to do that we use the negative of the delta HF value. The original equation has a delta HF value of negative 553.5 kilojoules per mole. But when we reverse the equation so that the cesium fluoride is being broken apart, we have to change the sign on our delta H so it becomes a positive 553.5 kilojoules per mole. Our second step is turning the metal from a solid into a gas. That's sublimation, and we would use the delta HS for that. Then we get to the single atoms of the nonmetal by breaking apart the bond. So if we have the fluorine molecule breaking apart into the 2 fluorine atoms, if we want to write our equation as 1/2 of the fluorine molecule going to 1 fluorine atom, we would have to divide our delta H by 2. If the bond energy for the F2 molecule is 158.8, we divide that by 2 and get 79.4. Then we have the step where we turn the metal atoms into ions. We take our cesium gas and turn it into cesium ions in the gas phase by removing an electron, and that step is using the ionization energy. We can turn the nonmetal atoms into ions using the electron affinity. The fluorine is going to gain an electron, and the electron affinity applies because it's in the gas phase. We would add up the delta H's from the manipulated equation if we needed to manipulate it, or just the original equation if we did not need to manipulate that particular step. And we end up with 756.9 kilojoules per mole. Again, this is basically just a Hess's law problem. We just have 5 steps. Anytime that we have an ionic compound, we're going to be using these same 5 steps. The way we manipulate the equation might change depending on the ionic compound. But the 5 steps of breaking the ionic compound into elements, turning the metal from a solid into a gas, getting the single atoms of the nonmetal, turning the metal atoms into ions, and turning the nonmetal atoms into ions will always apply. Calculate the energy change for the reaction, potassium, K, gas, plus bromine, Br, gas, yields potassium plus 1, K plus, gas, plus bromine minus 1, Br minus, gas. Given the ionization energy, IE, and electron affinity, EA, values in the table. Potassium, K, has an ionization energy of 419 and an electron affinity of negative 48 kilojoules per mole. Bromine, Br, has an ionization energy of 1,140 and an electron affinity of negative 324 kilojoules per mole. This question is a simplified version of the Born-Haber cycle. It is just using 2 out of the 5 steps. You have to figure out which atom you are using ionization energy for, which atom you are using electron affinity for, and whether or not you need to manipulate the equations and values for either of them. Is the answer A, 95 kilojoules per mole, B, 1092 kilojoules per mole, C, negative 95 kilojoules per mole, or D, 1092 kilojoules per mole? The correct answer is A, 95 kilojoules per mole. We're going to use the ionization energy of the metal, which is potassium, to turn it from neutral into a positive ion. We're going to use the electron affinity of the nonmetal, that is the bromine, to turn it from neutral into a negative ion. We just add 419 and negative 324, and that gives us 95 overall.